Okay, so now we're looking at Newton's third law. So to every action, there is an equal and opposite reaction. Or if an object A exerts a force F on object B, then object B exerts a force of negative F on object A. So the forces have just switched. So there's an action force A on B, and then the reaction force is B on A. And in the box it says it is important to remember that the action and reaction act on different objects and so cannot cancel each other out, and we'll talk about that in an example later. So we'll go through a few examples here. So we have gravitational force exerted by Earth on an object. So the action is, for example, a book. Earth exerts a force of mass times gravity, so it's our gravitational force on the book. And the book exerts a force of negative mg on the Earth. So when we drop a book, we can obviously see that the book is accelerated towards the Earth, but what's not so obvious is that the Earth is actually accelerated upwards as well towards the book. It's just that because the Earth is so massive compared to the book, the action or reaction is negligible. So obviously the book is not big enough to move the Earth, but obviously the Earth is big enough to move the book. Okay, and the little examples down the bottom talks about the moon's gravity causing tides and things like that, so feel free to read those through. Tractor pulls a sled, so the action force is tractor exerts a tension force T on the sled, and the sled exerts a tension force of minus T on the tractor. Okay. Book sits on table. The action is that the table exerts a normal reaction force on the book. Normal reaction force on the book. Book exerts a normal reaction of minus n on the table. So again, n and minus n have just switched. Car accelerates on the road, so the action force is the car wheels turn, exerting a friction force F on the road, and the road exerts a friction force of minus F on the car wheels. So these things, most people like these ones because they're pretty straightforward. Once you have an action, you pretty much just have to switch the two objects and make sure there's a minus sign. We had a positive sign before for the thing. So it's just a matter of practicing these ones, and there are exercises on these in your notes. A more interesting example here. So what is the error of the following argument? When a horse pulls a cart with a force F, there must be an equal and opposite reaction force of minus F. Since F plus minus F equals 0, so we've got the action and reaction forces, they just cancel each other out. The forces must cancel, and the horse and cart can never change velocity. Okay, so obviously this is not right, never change velocity, because horses can pull carts. So the questions I've asked over here is, why does the wagon accelerate? And then, why does the horse accelerate? So let's just focus on the wagon first. And if we've got the ground, we're going to assume that there's a negligible friction force between the wheel and the ground in this case. So the only force acting on the wagon in isolation is this force from the horse. Horse force. Okay, so we've got that one. And so why does the wagon accelerate? Because the only force acting on the wagon in isolation is that from the horse. Okay, this time for the horse, we can't really assume that there's no friction force because the hoofs here aren't made of the same material as our slippery wheel that goes over the ground without any friction. So we have got also horse pounds on the ground, so that's from the horse on ground. And we also have this way then the ground on the horse. That's our reaction force. Similarly, we also can't forget the wagon force here. Wagon force. So the horse is going to have a couple of forces acting on it. So basically, we've got these forces here, so the wagon force and the ground on horse. So we don't consider the horse on the ground because that's acting on the ground, not the horse. So we've got the wagon acting on the horse that way, and the ground is acting on the horse this way. So the wagon's acting that way, horse is acting that way. Why does the horse accelerate? Because the force, or when does it? The force from the ground is larger than the force from the wagon. Okay, so the thing that makes this difficult to understand for us is because we know that all the energy is being supplied from the horse. So to think about the ground acting on the horse is kind of like a bit of a mind bend for us. But just because of our Newton's third laws, if the horse acts on the ground also acts on the horse. And that's how Newton's third law can help us understand these kind of weird problems that also they seem like paradoxes sometimes. Like if you just looked at these forces here, then yeah, they look like they do cancel out. But if you just put these objects in isolation, then it starts to make sense. Oops, we'll get rid of that box for our notes. Let's get rid of that last one. Okay, great.